The atmosphere is composed of air. Air has mass. In fact, a column of air, 1 square centimeter, in an area extending up to the top of the atmosphere, has a mass of 1.2 kilograms. If the top of your head has a surface area of 150 centimeters squared, that means every time you go out and stand under the open sky, you have the pressure of 180 kilograms of air pushing down on you. That's like wearing a hat with a refrigerator on it. Is it safe to go outside? Don't worry, it's safe. The force applied by the air above you is called atmospheric pressure. Life on Earth has evolved into this high-pressure environment, so we are able to handle the pressure just fine. In fact, most of the time we are totally unaware of the pressure. We do feel the air pressure when it changes quickly. Have you ever traveled to the mountains and noticed the popping of your ears as you go up or down the mountain? Sometimes this happens in an airplane when it changes altitude rapidly, or in a car going up and down a hilly road. If you have ever had that experience, keep it in mind as you think more about atmospheric pressure. Sometimes you can see evidence of change in pressure even if you can't feel it. In an airplane, you might notice that the packets of peanuts or chips are puffed up like balloons. This bottle of air appeared uncrushed when it was sealed at high altitude. Then it was brought to sea level. Its flattened look is evidence of change in air pressure. What causes air pressure? Air particles have mass, so they are pulled to Earth by gravity. The air surrounding the Earth has weight. Atmospheric pressure is the weight of the air pushing on Earth's surface and everything near Earth's surface. Remember, air particles are zipping around individually, so what prevents gravity from attracting them all to the ground? Why aren't we all walking around knee-deep in a soup of oxygen and nitrogen particles? The answer is kinetic energy. Kinetic energy is the energy of motion. The gas particles have so much energy of motion that they are bouncing each other around in all directions. They resist being compressed by this constant banging into one another at an astounding rate of 1 billion times per second. Here's an important point. The atmospheric pressure is not only pushing down on Earth, the particles are also banging around and colliding with the air particles above and from the sides. As a result, atmospheric pressure acts with equal force in every direction. But atmospheric pressure is not the same everywhere. Air pressure is caused by the mass of air being pulled to Earth. So what happens if you go up into the atmosphere, high above Earth's surface, where there is more air below you and less air above you? If you have the good luck to go for a hot air balloon ride, you might find yourself 2 kilometers above the land. Up there, 2 kilometers of air is below you, so that 2 kilometers of air is not applying pressure up where you are. Therefore, the atmospheric pressure is less at that altitude. Because we live at the bottom of a sea of compressible air, the atmosphere is most dense at Earth's surface. At the surface, with the greatest amount of air overhead, we have the greatest pressure. The air particles are squeezed close together because gases can be compressed. And when more particles are present in a given volume, the gas is more dense. The air becomes less and less dense the higher you go into the atmosphere. As you go up into the atmosphere, pressure decreases, the air expands, and the air gets less dense. Mount Everest is over 8 kilometers tall. Up on top, the atmospheric pressure is only 1/3 of the pressure and density it is at sea level. Have you ever seen pictures of climbers laboring up the highest reaches of the mountain? Most of them are using oxygen supplies. Why? Because there is only 1/3 as much air in each breath at that elevation, so only 1/3 as much oxygen. It takes an exceptional climber to reach the summit without extra oxygen. Now, about those ears popping. When you travel through the mountains, does it have anything to do with atmospheric pressure? First, let's find out how atmospheric pressure is measured. Measuring air pressure. The air pressure that meteorologists talk about on an evening news is caused by the mass of air pushing down on a certain point on Earth's surface. Elevation is one factor that causes pressure to vary, but there are a number of other factors as well. These factors and the resulting pressures are of interest to weather forecasters. Meteorologists use a barometer to measure air pressure. An Italian naturalist named Torricelli invented the first barometer in 1643. He filled a long glass tube with mercury and turned it upside down in a dish also filled with mercury. A small amount of mercury, not all of it, ran out of the tube and into the dish, leaving an empty space above the mercury. This space was a vacuum. A vacuum is a space containing almost no matter, not even air. What was holding the heavy column of mercury up in the tube? Atmospheric pressure. Air pressure pushes down on the mercury in the dish. The pressure is distributed throughout the mercury, including the mercury in the tube. Remember, one column of atmosphere with an area of 1 square centimeter has the mass of 1.2 kilograms. If the column of mercury is 1 square centimeter in cross-section, it will have a mass of, that's right, 1.2 kilograms. So the force of air pressure is exactly balanced by the weight of the mercury. As Torricelli observed his new invention closely, he noted that the level of mercury moved up and down a little from day to day. He reasoned that the changing level of mercury was due to the changes in atmospheric pressure. If atmospheric pressure increases, there is more pressure on the mercury, so it rises further up the tube. Torricelli had invented the first barometer, an instrument for observing and measuring changes in atmospheric pressure. Today, meteorologists often use another type of barometer called an aeronoid barometer. Aeronoid barometers are much smaller and more portable than mercury barometers. At the heart of an aeronoid barometer is a sealed bellows-like chamber with a spring inside. All the air is removed from inside the bellows. As atmospheric pressure increases, air particles bump into the bellows more frequently. This compresses the bellows and the device becomes shorter. On the other hand, low pressure means less frequent hits from air particles, which allows the bellows to expand. A pointer attached to the bellow moves along a scale to show the change in air pressure. Modern barometers are digital. They use electronic pressure sensors and circuits that produce digital displays of atmospheric pressure. If an electronic sensor and a transmitter are attached to a barometer, air pressure information can be radioed from the weather balloon back to the receiving unit on Earth. That's how we collect information about air pressure at high altitudes. When you packed your suitcase at home and included a half-filled bottle of lotion, the air pressure inside that bottle was equal to the air pressure on the ground. As it rides in the airplane up to the top of the troposphere, 80% of the atmosphere is now below, so the pressure inside the bottle is greater than outside. When you open that bottle, air will rush out and force the lotion along with it. A bottle with air in it is actually a simple barometer. Scientists and meteorologists use several different units to report pressure. For historical reasons, inches or centimeters of mercury are used in science experiments. Meteorologists, on the other hand, look at the average atmospheric pressure at sea level and call that 1 bar. If you are relaxing at the beach, the pressure around you will be 1 bar, or close to it. The bar has been subdivided into 1,000 equal parts called millibars. These are the units you use to record your local atmospheric pressure on the class weather chart. In practice, standard pressure is actually 1,013 millibars. Any pressure below 1,013 is lower than normal pressure, and over 1,013 millibars is higher than normal pressure.